recording. Okay. Okay, so I'll just say one one last thing about projections. So maybe I should wait. Is Brennan? So everybody okay to start again? Okay, excellent. Okay, so I'll say one thing. So this was, you can see this is a dot cross complex. So one thing you can see is that the cross product has something to do with the projection. So if we take like an A vector like this and a B vector like this. So if we project one vector at a right angle onto another vector and find out what the length is, that we can call that the P, like the projection onto a vector. And so what does the P equal? Well, the P equals the length of A times the cosine of that angle. So here's that angle. So that's the hypotenuse times the cosine. The cosine tells you the length of the adjacent side of the triangle. So that's the projection, but the dot product is more than the projection. So the dot product is the projection scaled by the length of the other vector. But in the special case, so case where the length of B equals 1, then it's exactly the projection. So in that case, the dot product would exactly be the projection, because you would be multiplying this thing times 1. The length of, because remember the definition of the dot product was the length of A times the length of B times the cosine of the angle between them. And so if B is 1, then the projection, the dot product exactly equals the projection. But the dot product is more than the projection because you have to multiply by the length of B. So it's scaled by B. So it's not just the angle between the vectors, the lengths matter too. Okay, so it's related to a projection, but it's more. Okay. So now let's go back to the Bloch equation. So you want to go back to the Bloch equation and just see, so what does that mean? So if we put the Bloch equation, sort of a diagram of our basic Bloch equation. So the first thing we'll do is have the direction. So this is the B field. So this is a relationship between two magnetic fields. So M is a magnetic field and B is a magnetic field. And so this says for a small amount of time, the vector that tells you how to change the bulk magnetization is equal to the cross product of whatever the bulk magnetization currently is, multiplied, so cross producted with the B, whatever the B currently is. Now, both of these are actually, this is actually sort of the magnetic field vector at a particular point in time. So as usual, the mathematicians, they would leave out things like that because it sort of clutters up the thing and that clutters up their thinking. But this is changing at every moment in time. And same with this one. that potentially could change at any moment in time. So the B could change at any moment in time. But it could also change at any point in space, right? So remember, there's like sort of an X, Y, Z in here too, because that's going to be different at different points in space also. But let's forget about all that and just say, at this point in space, this is what the B is. And then at this point in space, this is what the M is. So here's our M. Now, it could be exactly the same, but I just drew it sort of not exactly the same so we can see something actually happen. At any moment in time, it can be sort of any direction, because remember, the M was just, the vector sum of all those, all these guys that are at some angle around those two cones. So we just do, vector sum, and that gives us M at any one point in time, at any one point in space. Okay, so now let's see what this equation says. So this equation says, if we want to figure out the vector that tells us how to update this, we cross product these two guys. And so if we cross product them, what do we get? We get a little vector that sticks out like this. Now that vector is going to be perpendicular to this guy, and it's also going to be perpendicular to this guy. So think about that. You've got like these two vectors there, and they define a plane. And so then sticking out perpendicular to that plane, there's going to be a little vector, this dm dt vector. So that doesn't help us down there. So notice that what it's going to do is, this is how the m vector changes. So we need to add this change into the m vector. So here's the m vector, and so you can think of it as, you just draw it, not in front, I'll make it. So here's the m vector right there. Okay, so how is this going to change the m vector? It's just going to add to it. And so if we just take this guy and paste him up there, like that. So this guy is dm vector dt. So what is the vector that tells us how the m vector changes in a small amount of time? And then here's the actual m vector itself. And so what does that say? That says at a slightly later point in time, we're going to get this vector, this dotted one. So this is, m vector new. So there's the new m vector. Now we just do the same thing again, because this is a differential equation. It tells us for each instant in time what's going to happen in the next instant in time. So if we run the equation again, what's going to happen? Well, the m vector will have rotated a little bit, basically, around that circle. Will have rotated a little bit around the circle, and so when we calculate the next dm dt vector, it will also rotate. So it's going to rotate a little bit like that. It won't be the same, because remember that the cross product is going to be perpendicular to whatever the new position of the m vector is. And so what will happen? Well, the next time we update it, it's going to be pointed slightly more around the circle. And so this is basically exactly the same equation for a top. This describes that precession pattern of the top. And so, sorry, I didn't mean to draw it up. We'll just put it like this, right along the circle, but slightly angled different than this last guy. So if you keep doing that, what it'll do is it will just basically just go around the circle. Now it won't change, notice it won't change any other aspect of the vector. It's always going to be perpendicular to both of these guys. And so it won't change the length of the m vector. This operation doesn't change the length of the m vector. It just keeps the length of the m vector the same. So when we get to the other terms in the Bloch equation, we'll see that those terms in the Bloch equation actually do change the length of the m vector. They can sort of, shrink it down, make it grow, and so they can move it in any direction. So it doesn't have to be just along the circle. But this part of the Bloch equation just explains the precession part. And we only considered it in a very fixed case where we have, a fixed b, and nothing else changes m. So if we have a fixed b and nothing else changes m, then we get precession. Precession forever. So it will just continue to go around forever, won't change. And I can see from that, so I've said these cones, remember, when you're actually in the real magnet, here's the real magnet, the cones are like this. Because remember, the B0 field sticks out, the real B0 field sticks out, is parallel to the floor. So this direction is parallel to the floor. Okay, so any questions about this? So what we did was dot product, cross product, complex multiply. We didn't use complex multiply because that's going to be basically for the Fourier transform. But it's good to put it in here so you can see how it's kind of related but different than the dot product and the cross product. And then we used the cross product to sort of like try to understand the first term of the Bloch equation, which is the term that describes this angular momentum. And so that and that first term explains the precession movement, which is very similar to the movement of a top. And so the other thing to make sure, any questions, I have to remember always to look at the Dalai Lama. Are there any questions about the other aspects of the class, about the assignment, like the MATLAB assignments? I put up that MATLAB 0 assignment just to sort of mess around with some MATLAB functions. So you should go ahead and do that, get MATLAB installed. So that's going to take a little while and just sort of mess around with it, get familiar with it. And then any questions about the paper? So remember the paper, the idea of the paper was go to the original neuroimaging literature, sort of the neuroimaging techniques literature, and dig out an original modern paper. It could be an older paper too. And just try to understand one paper, just a review pretty much of one paper in the original literature, and by looking up some of the references in the paper to try to figure out where that line of research came from. So